Hello everyone, welcome to Reactify Labs. Today we will talk about a very important topic called cash. We all know what cash is. If not, then we will all know by the end of this video. So, in short, cache is basically a faster storage. So, if you have, let's say, a very big memory and you have to frequently access it, then it will take too much time. So, that's why we keep a smaller memory and where frequently accessed items are stored so that we can quickly retrieve from this. What is the best real life example of this? The best real life example of this is your home. So let's say there are a few things. For example, let's take an example of blanket. Let's take an example of a suit. And now take an example of a t-shirt, comb. So where do you store these things? In your home, obviously, but where? So see, blankets, suits, these are some things which we wear or use occasionally. Blankets we use generally during the cold. Suits we use when there is some occasion. Okay. So we usually store blankets and suits in our almirah, right? Or some big storage because we don't use it often. And even if when we have to use it, we have to go open the umbrella and search where it is. This takes time, right? Important documents also, safe documents, gold, jewelry, these things we keep here so that because we do not use it very often and it also takes time to actually retrieve. Actually not, this is not relevant. It's just that we use it very infrequently, so we do not keep them all in open or outside. Okay. Contrast to that, we have t-shirts and comb. T-shirt we use daily, like some 5 or 6 t-shirts. So we keep it in our, let's say, small cupboard kind of thing or a wardrobe. We store it here. We have, let's say, what do you call, a dressing table. Usually we store our comb here. So the storage size, if you see, of wardrobe and dressing table are very small compared to this, right? So that's why we want quick retrieval of these items. We don't want to just go open, search through all the items to find a comb or a t-shirt, right? So that's why we store our t-shirt in wardrobe, comb in dressing table for quick retrieval, because we know that we use it daily, we use these things daily. So that's why we have cache. Cache plays a similar role as our wardrobe or dressing table because it knows that it has to store frequently accessed elements, because frequently accessed elements are accessed very frequently, very quickly, one after the other, like that, right? One more thing which I would like to point out here. Let's say this is suit. Okay. So this suit, it's not like we just bring the suit from the market and we put it in the almirah. Instead, what we do is we keep it outside. Outside as in maybe in our room somewhere behind the door for a few days or 1 or 2 days, because we have just bought it. We may not be very sure, or we have to maybe use it quickly. So that's why we keep it outside. We use it, we test it maybe 2 3 days, and then we go and put it inside the almirah because we now know that it will be used after many months now. So this here is called it has a name in caches which is called temporal locality, because we have got this quickly, so we are going to use this quickly. So that's why temporal locality. And spatial locality is something we will talk about later. So I just thought of this, so I thought let's bring it here, the application of temporal locality in our day-to-day life. So now everything is explained. You have an idea of how caches work, why caches are required. Let's go into the technical definition of caches. Okay. As the technical definition goes, A cache is a smaller, faster storage location. As I talked about, it's a storage, just like your dressing table, just like your wardrobe. Storage location that temporarily holds copies of data from the main storage. Such as RAM or frequently used instructions. Okay. To provide faster access to the data that is likely to be needed in future, thereby reducing the need to access slower storage locations, so that we don't have to go and access these slower storage locations, we are provided with a cache. Okay. A CPU cache situated close to the processor stores recently accessed data or instructions for rapid retrieval. Just an example. Now let's talk about what are the different types of caches. Okay. So if we talk about types of caches, we have first L1 cache, and then we have L2 cache, and as unobvious as it may be, we have L3 cache. So level 1 cache is the smallest and fastest cache directly integrated with the CPU. An L1 data cache stores recently accessed data and L1 instructions. An L1 instruction cache holds frequently used instructions. So generally these are for instructions. Okay. An L2 cache is larger, means it's larger than L1 cache. It's located between L1 and main memory and offers additional storage capacity as compared to L1. An L2 cache may store a larger set of data and instructions than L1 and providing faster or more flexibility. L3 cache is shared among CPU cores or processors. In multi-core processor, L3 cache facilitates data sharing and access among cores. I am not going to go more detail into these because these are not relevant as an engineer, as interview perspective, because these are mostly used when we are actually designing chips or hardware. That's when we should know about these caches and their performance. So I'm not going to talk more about these. Okay. Let's move towards what's more important. Let's talk about some of the cache replacement policies. So if we talk about replacement policies, first one is LRU. LRU stands for least recently used. So it replaces the cache line that has not been accessed for the longest time. A program accessing data less frequently may trigger the replacement of the corresponding cache line under LRU. So basically, let's say our cache size is 4. Let's take an example. It has 4 elements, 4, 3, 7, 9. Now, next number, let's say, comes as 7, not 7. Let's say next number is 7. Then what happens is we see that 7 is already present. So, okay, actually, let's do it in this order. First, what we got was 9. Next, we got 7. Next, we got 3. Next, we got 4. Okay, that's why 4 is at the front. Okay, now let's say the next number again we got is 7. So, what happens is this 7 gets replaced from here and get put here. So, now 7 comes here. 4, 3, 9. Let's say another number comes 3. Now what happens is 3, 7, 4, 9. Now let's say some new number comes. What is that? 8. It is not present. So 8 comes. So where will 8 go? 8 will go in the front because it's the number which has come recently. 8 will come here and 3, 7, 4 will go, and 9 will be replaced because we can see that 9 has been not been used recently. Okay, 9 is something which has been least recently used. 7 has been used more recently, 3 has been more recently used, and 4 has also been used more recently than 9. That's why when 8 comes and we had to replace something, we replaced 9 because 9 was least recently used. So that's all about least recently used policy. Next is FIFO. FIFO is first in, first out. So again, if we take the example of 9, 7, 3, 4, so here will be 9, 9, 7, 3, 4, and now let's say 7 comes. So then what happens is just 7, it will check that 7 is here, it will not do anything, it will not change the order. Again, for when 3 comes, 3 will remain as it is. But when let's say something like 8 comes, then it says first in, first out. Who was the one which came first? So we see that 9 had come first, so 9 will be replaced now. Even if 9 had come before 8, it's still least recently, according to least recently used, 9 would not be replaced then, right? But here again 9 will be replaced because it was the one which has come first. So that's all about FIFO. Now there is one more called most recently used. Most recently used. So most recently used is again just opposite of least recently used. The one which has been used most recently will be removed. There is one more called LFU, which is least frequently used. So what is least frequently used? So here we will see which has been used least frequently. So again, when we go with 9, 7, 3, 4, so we have 4, 3, 7, 9, and we see, let's say 9, 9, 9. 9 has been used thrice. So 9 we know. Now let's say 7 is used, 3 is used, 4 is used. And now 8 comes. Now we have to replace. Then we will see that 9 has been used 4 times. So we cannot replace 9. And 7, 3 and 4 have been used 2 times. So we can choose one of these to replace. So this is what least frequently used is. Even though 9 has been used least recently among these, but still 9 has been used more frequent number of times. That's why it will not be replaced. And in the end we have a random replacement. So here we are assuming that any number can come anytime or anything can come anytime. So we will just randomly replace anything and assume that it will perform as good as any other algorithm. But what we should do while choosing our replacement policy, we should take a call depending on what kind of data we are holding and what kind of replacement policy would suit us the best. Okay, great. Now let's talk about some of the cache write policies. Write policies. First one is write through. So write through is a caching write policy that involves updating both the cache and the underlying database simultaneously for every operation. Okay, updates cache and DB simultaneously. So as the name suggests, or as the definition suggests, so we have a cache, we have a DB. Somebody needs to write something, so it will write to both cache and DB. Okay, so this is what it is. It's as simple as that. The write will go through the cache to the database. So both cache and database will write. Characteristics are each write operation triggers an immediate update to both cache and database. It ensures that the data in the cache is always synchronized with the data in the database Obviously, as the definition suggests, cache and data will always be synchronized. The cache will not have stale data at any point, right? Advantages: it guarantees data consistency between cache and database. It minimizes the risk of data loss in the event of cache failure. Uh, Actually, I'll write it down so that it's more clear. So if we talk about characteristics, it's actually characteristics is clear from the definition. I'll write about advantages. I'll just reiterate the characteristics. Each write operation triggers an immediate update to both cache and the database. It ensures that the data in cache is always synchronized with the data in database. Okay. DB and cache always synchronized. Okay. Now let's talk about advantages. First advantage is data consistency. Data consistency between cache and DB. And next is minimizes the risk of data loss. Data loss risk minimized when in case of cache failure. Okay. Considerations: there are a few things we need to consider. May introduce higher write latency due to synchronous nature of updates. We have to update database also. Database is huge, right? Generally database size is much more than cache, so database update will take more time as compared to cache. So higher latency. And it can be resource intensive as well. Resource intensive, especially in scenarios where we have too many writes. If high write frequency is there it will be resource intensive. So it is suitable for applications where data consistency is critical, such as financial transactions or real-time updates. Right? So basically these all come under use cases. So this was all about write through. Let's talk about another write policy, which is called write back cache policy or write behind policy. So this is write behind. It is also called write back. So this is a caching write policy where cache is updated first and then the database is asynchronously updated at a later time. So cache is updated first and then the database is updated asynchronously. Is asynchronously updated at a later time. When we say asynchronously, it means obviously it will not be at the same time. So the characteristics include write operations first update the cache, thus allowing for quick responses to write requests. If we have write requests, we do not need to wait for the database to get updated as in write through policy. You will just update the cache and the write will go through. You will just update the cache and the write will go through. Asynchronous updates to the database occur at a separate pace, often during the periods of low system load. So when we have low system load, then we will take care of updating the database. So again, that is also something which we have an advantage while using this policy if our requirement is like that. So what happened? Okay, let's talk about advantages. So advantages include reduced latency, reduced write latency as write operations are acknowledged as soon as the cache is updated and we do not need to wait for database. And second one is can handle bursts of write activity more efficiently. Can handle bursts of write activity more efficiently. So even if there are too many writes, it can be handled because cache gets updated quickly and it responds, allowing for the further writes. So if we talk about considerations, there is a risk of data loss. Data loss risk. So increased risk of data loss in the event of system failure before database updates. It is possible that the write is in cache and there is a failure and write has not propagated to the database. So all the updates will be lost. And it requires careful management of asynchronous update process. It requires careful management of asynchronous update process. And if we talk about use cases, so suitable for scenarios where low write latency is crucial and occasional data loss is acceptable, such as caching in web applications. So if we have to cache web applications, we don't care about database. So here write back policy is the best. Okay. Now let's talk about another cache writing policy, which is write around policy. Mm, okay. So this one is write around. What is write around policy? So this is a caching write policy where data is updated only in the database by passing the cache. This approach invalidates the cache for the updated data. So here what happens is there is a database, actually not like this. There is a database, there is a cache. So what it does is data is updated only in the database. When a write needs to happen, it will just come to the database, it will write to the database and invalidate the cache. It will say that whatever is present in the cache is now invalidated, and later the cache will be updated from the database. Okay. So data is updated only in the database. Data is updated only in the database by passing the cache. By passing the cache. So it invalidates the cache for updated data. Invalidates the cache for updated data. So write operations skip the cache entirely and update the data directly in the database. Cache entries for the updated data are marked as invalid. So the entire cache entry is not invalid. Only the thing which got updated is now stale in cache and that gets invalidated. Rest all remains the same. So what are the advantages? So the advantages include it minimizes the impact on the cache, avoiding unnecessary caching of infrequently accessed data. Okay, avoids unnecessary caching, and it reduces the risk of cache pollution with data that may not be reused. Reduces cache pollution. It is possible that some data may not be used ever, but still they are present in cache. In those scenarios, this policy is good. So, what are the things we need to consider? Read operations for recently written data may experience higher latency because we have to write in the database. So, higher latency. And next is effective for scenarios where certain data is written once and never accessed again. Okay, so lower rights maybe. So if we have some kind of data which are rarely accessed, so for that this policy is good. Use case is useful for scenarios where certain data once written is unlikely to be accessed again in near term, such as logging or archival systems. So use cases, archival or logging systems. Okay, so this one was right around policy. Next policy is refresh ahead. Refresh ahead policy. So this involves proactively refreshing cache entries before they expire, ensuring that the data is readily available when accessed. So the entry the entries before they expire are refreshed, like refreshed from the database. So before expiring, that's why we're calling it refresh ahead. So ahead of expiring, we refresh the cache. So if we write, it involves proactively refreshing cache entries. Proactively refreshing cache entries before they expire. Before they expire. Okay. Ensuring that data is readily available when accessed. Characteristics are the cache manager anticipates the expiration of cache entries and refreshes them before they become stale. It reduces the likelihood of cache misses for frequently accessed data. If some data is frequently accessed but they expire, it needs to be fetched again from the database, and that is something which is taken care by the refresh ahead method. Let's talk about the advantages. Improves cache hit rates by proactively refreshing data. Improves cache hit rates. And it mitigates the impact of cache misses. Mitigates the impact of cache misses. So you might ask, why do we call it a write policy? We are not writing anything, right? But yes, we are writing. When we say we are refreshing, it means fetching it from the database, or refreshing it. It means we are actually taking the data from the database and writing to the cache, right? So effectively we are writing to the cache. Database is something from where we are only reading, but our policies are cache write policies. So we should know how the data is written to the cache, and this is how it is written to the cache. Okay. So advantages are done. Now let's talk about considerations. It requires a mechanism to predict which cache entries are likely to be accessed soon. Need a prediction mechanism. So it requires a mechanism to predict which cache entries are likely to be accessed soon. It can consume additional resources to refresh entries that might not be accessed. Additional resources. So there might be additional resources to fetch. It is suitable for scenarios where predicting and proactively refreshing frequently accessed data can significantly improve overall system performance. Okay, so this is all good. Now let's talk about something which is really important, as point of view of system design interviews, because we rarely have a single cache, right? These all are good just to say that okay, there will be cache, but if you see, there will be any system, if there are caches, there will be a load balancer. It means there will be multiple caches and data will be distributed across different caches. So what we are going to talk about now is distributed caching. So what is distributed caching? Distributed caching involves the use of caches spread across multiple nodes or servers in a network. As the name suggests, the cache is distributed. So what are the benefits of it? First one is scalability. Because the caches are distributed, it can scale, it can handle large amount of loads, and they are fault tolerance. There is no single point of failure. So if they are distributed, it means even if one system fails, one cache fails, other one will handle the load. And what are the popular examples? The popular examples are Memcached and Redis. So these are the examples of popular distributed caching systems which are used to optimize performance in large-scale distributed environments. Let's talk about just two more things now. Cache coherency. I'll quickly talk about the things here. Cache coherency. What is cache coherency? It's a critical concept in distributed caching that ensures that the same data cached on multiple nodes remains consistent, right? Because if we have multiple cache nodes, we need our data to be consistent, right? The one that is here, everything needs to be consistent. As we were talking about in the, what do you call that, cap theorem or strong consistency, eventual consistency, we need consistency. But how that consistency is achieved? Till now we have only talked about consistency, but we don't know yet how that is achieved. Let's talk about how that is achieved in caches. So first we will write down what cache coherency is. It's a critical concept in distributed caching that ensures that the same data cached on multiple nodes remain consistent or are consistent. So for this, we follow some protocols. One protocol is MESI. MESI is modified, exclusive, shared, invalid. It defines the possible states a cache line can be in to maintain coherency across multiple caches. So MESI stands for modified, exclusive, shared, and invalid. So it defines the possible states a cache line can be in. It defines the possible states a cache line can be in to maintain coherency across multiple states. So what is M? Modified. This cache line, it says that if, let's say, something is marked as M, it means that this cache line has been modified and is now different from the corresponding line in main memory. So there is a cache, there is a main memory. And if some entry in cache is marked as, let's say, M, it means that it is modified. Now it's different from main memory. When it's marked as E, it means the cache line is exclusive to a single cache and has not been modified. It means there may be different caches, but this one is exclusive to this cache and it's not modified. Shared, if something is marked as S, it means the cache line is unmodified and it's shared among multiple caches. Okay, this means multiple nodes also share the same value. And I means invalid. This cache line is invalid or stale and the data in it cannot be used. If it is marked as I, it means this data is invalid. You have to fetch it again. Okay. So this was MESI protocol. Another protocol that exists, that is used, is called MOESI. It's similar to MESI, MOESI. M is modified, E is exclusive, S is shared, I is invalid. There is only one O, which is called owned, which is different from MESI. So this cache line is not only exclusive, but it is known to be unmodified in other caches. If something is O, it says that this is exclusive as well as it is unmodified in other caches. This state optimizes write back operations. So if we have this MOESI protocol, it optimizes write back operations. How? Let's understand with an example. Imagine a scenario in a distributed caching environment with 3 nodes. There are 3 nodes, A, B, C. Each node has a cache containing a specific piece of data. Let's say there is data D. When node A modifies its cache data, the protocols ensure that B and C are informed of this modification. If D is D1, so this and this both will be informed. Node A modifies its cached data. Now node A is modifying, it's now D1. The protocol ensures that node B and C are informed, and the corresponding cache line transitions to invalid or shared state. The invalid or shared states prevent nodes from using stale or outdated data. So due to the presence of O, what it does is A is updated. It means A is the owner of the data, and now B and C got invalid tag. It means the data that you have is invalid. Okay, and if it is invalid, it cannot be used. So what they need to do is they need to update it to now D1, and now when it is D1, it means it has the updated value, and now they can be used, right? So this is almost done. Just one quick thing, the real world examples where caches are commonly used. There are web browsers. Web browsers utilizes cache to store frequently visited web pages, reducing load times for users. There are database systems. So database systems also use caching to speed up query responses, enhancing the overall system performance. So that's it. I hope this gives you a good understanding of everything about cache. I know this video was long, or it is long, but I have covered almost everything that's there to know about cache. So it will be helpful for your interviews. It will be helpful for your university exams also, if there is one. So that's it. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.